In this chapter, we're going to talk about conformers. What are conformers basically? Conformers are the same compounds that have different spatial arrangements. For example, we're going to draw here for you ethene. So as you remember, ethene was C2H6. I'm going to draw you the perspective arrangement of this compound. In order to draw this, now as you see, as always, we're going to start with the main chain, which is 2 carbon attached to each other with a bond, with a single bond, and we show that with a line. Now to draw the hydrogens, since we're going to go with a 3D shape, there are some hydrogens that are going toward us, coming outside the page. We're going to draw those with a wedge basically. A wedge is, whenever you see wedge, that shows the substituent coming toward you, is coming outside the page. Now there are some hydrogens that are going inside the page. These ones we show with dashes. Some people refer to it, some textbooks refer to it as hashes. Doesn't matter. And we're just going to have hydrogens that are going upward. So as you remember, this is tetrahedral, so the angle between each of these hydrogens is 109.5 degrees. So we're just going to, it is not that accurate, but you get the idea of what we have here. So this shows you the 3D shape. Now I know, right now we have all hydrogen, but if we had another substituent, that would have mattered where the specific substituent is. Imagine if it was a methyl group, chlorine, or fluorine. So this is called a perspective structure. Now imagine if we were looking at this perspective structure, since it is a 3D structure, imagine if we were looking at it from the left side, where I draw the eye. So if we look at it from the left side, we see the 2 carbons aligning with each other. One is trying to hide behind another one. So the one that is in front of you and you see directly on the left, we draw that with a dot. And the one that is going to be behind it, that we can barely see, or sometimes it can hide, we draw that with a circle behind the dot. So the light blue that I'm drawing the circle with, as you see, that is the carbon that is on the right side of the perspective structure. So as you see, in these 2 carbons, the hydrogens that are attached to it, these 6 hydrogens are basically in alignment with each other. So you see there are 2 hydrogens coming towards us from downside, 2 hydrogens are going upward, and 2 hydrogens are going inside the page a little bit towards the bottom. So in the Newman structure, we attach 3 hydrogens, one from above, from the top side, one from bottom right, one from bottom left. And the same applies to the carbon behind. Now we're going to attach those hydrogens to the circle. And we make sure that doesn't touch the dot, because that doesn't mean that it's attached to the carbon in the back. If you attach it to the dot, that means you're attaching it to the carbon in front. And that is impossible, because carbon can only make 4 bonds. So going back to conformers, conformers were basically the same compounds having different spatial arrangement. So basically these 2 carbons are attached to each other with single bonds. So due to CC rotation, we can basically rotate one of the carbons and make a different spatial arrangement for this compound. So in this case, in the Newman structure, we keep one of the carbons, which usually we keep the carbon that is in front of us, we keep that fixed, and we start rotating the one that is behind the carbon that we see directly, which we draw it with circle. So I'm going to show you how the rotation happens here. Now, in order for you to see how the trend goes here, I'm going to write the hydrogen that is attached to the carbon in the back, the top one. I'm going to label that with red, as you see here. So basically I'm going to copy the same Newman structure that we had before. I'm going to put it here, and we're going to rotate this 60 degrees. As you rotate the 60 degree, the hydrogens attached to the carbon in the back are not going to be aligned with the hydrogens attached to the carbon to the front. So we're going to draw the same thing for the carbon in front, hydrogen on the top, lower right, and lower left. With the circle this time, the red hydrogen, since it was rotating 60 degrees clockwise, we're going to draw it on the top right. And the second hydrogen is going to go at the very bottom. And the third hydrogen is going to go top left. If you rotate it another 60 degrees here, we basically go back to where we were in the first structure that you see. So they're all going to align again. But this time the red hydrogen is going to go behind the one at the bottom right. So we're going to, as always, we're going to draw the fixed arrangement of the carbon in front, the hydrogen on top, bottom right, bottom left. And since we rotated 60 degrees, the carbon in the back, we just align all the hydrogens again with each other, as you see here. Now if you rotate it another 60 degrees, you can see basically we're going to have something same as a second structure, but this time the hydrogen is going to go, the red hydrogen is going to go at the very bottom of the structure. And basically the other two hydrogen are going to be at the top left and top right of the structure. The structures that have the hydrogens, or in other words substituents of both carbons aligning with each other, we call those eclipsed, such as the first structure and the third structure. As you see here, all the hydrogens are in alignment. Those that the substituent, or in this case hydrogens, are not in alignment and they have like 60-degree angles apart from each other, we call these ones staggered, like the second one and the fourth structure. These ones are usually more stable energy-wise, because as these atoms, as these substituents are trying to be as far as possible from each other, staggered arrangement is going to help them to stay apart from each other as much as possible. Now hydrogen, I know hydrogen is not really a big deal here, but still, even with hydrogen, staggered arrangement is a lot more stable than eclipse structure. So basically, if they ask you, eclipse structure has the highest potential energy, while staggered has the lowest potential energy and is the most stable one. Now for you to better understand, I'm going to draw a diagram of potential energy. Now the x-axis is basically the degree of rotation that we already have. So we go from 0, 60, 120, 180, and 210. And the y-axis is the amount of potential energy that we have. So as you remember, if it was 0 degrees, it is the first structure that is eclipsed. As I told you, eclipsed structure has higher potential energy and it is more unstable than staggered. So we're going to show it with green. The staggered, however, is going to have a lower potential energy due to being more stable. Now we're going to mark it a little bit lower than eclipse. Now this is a hypothetical diagram, but in the real life, this is how the diagram usually is. As you see, the orange one is a staggered. Now if you rotate it 120 degrees, it's just going to go back to eclipse in the third structure, as you see. So it is going to have the same amount of energy. So we make sure it aligns with the first one. If it is 180 degrees, it's basically staggered again, the fourth structure, and it's going to have a lower potential energy. The 210 is going to be eclipsed. I didn't draw it here, but you should know. Once you rotate a staggered structure 60 degrees, it's going to go back to eclipse. So it's going to have the same potential energy as the first and third structure. So in between, as you see, I'm going to draw it with a pink line. This is a trend of potential energy as you rotate the conformers. In the next example, we're going to go with butane, CH3, CH2, CH2, CH3. And we're going to analyze it with a single bond between the second carbon and the third carbon. So I'm just going to label them with 1 and 2. Now we're going to draw the perspective structure first. So as you see, as I always told you, you draw the main chain, which is basically the two carbons. And there's always going to be one substituent coming towards you. So we're going to show that with a wedge. And it's good to give wedge a little bit of angle. Don't draw it straight to the bottom. Try to draw it either to the bottom left or bottom right. The substituent going inside the page is going to be shown with dash, as I told you already. And you can make this one horizontal. No one cares. If you do the wedge, you basically draw the dash with regards to the wedge. And there's always going to be one substituent parallel to your position, which is going upward. So in this case, we have two hydrogens as substituents to these carbons and one methyl group. And we're going to put the methyl groups on top, as you see. So this is the perspective structure of butane. Now if you look from the left side again, where I draw the eye, we look at it, and I'm going to label the carbon in the back with green so you can have a better idea. So the carbon in front of you is going to be a dot again with substituents attached to it. The front carbon is always going to have a fixed position. So one substituent going up, one substituent going bottom right, one substituent going bottom left. Since I showed the carbon on the right side of the perspective structure with green, I'm going to draw the circle in green so you can have an idea of where the second carbon is again. Now we're going to put the CH3 on top, and it's basically what the red eye sees on the left side. Now the hydrogen on the bottom left and bottom right. So in this case, since it is eclipsed again, we're going to draw the methyl group attached to the second carbon aligned with the methyl group attached to our frontal carbon, or the one on the left of perspective structure. And the hydrogens aligning with the other hydrogens, as you see here. So as you see, this is the perspective structure, as we said. And this one is a Newman structure. So we're going to do what we did in the last example. We're going to rotate it 60 degree by 60 degree to see what kind of spatial arrangement is going to give us. So we're going to basically draw the Newman structure, the same thing that I already draw for you, but this time I'm not going to show the ring with green because you already know it is the carbon in the back. And as I told you, when we rotate, we just rotate one of the carbons, and it's always going to be the one in the back. It is not wrong if you do the one in front, but you're just going to confuse yourself. So let's always go with the one in the back. It's a lot easier, and since it is a circle, it's not going to be that much of a pain to rotate it. We drew this now. We're going to rotate the carbon in the back 60 degrees. So front one is going to be fixed. We draw basically the top, bottom right, bottom left structure, and we're going to draw the circle with a top left, top right, and bottom attachments. So this time, as you see, the CH3 attached to the carbon in front is going to be fixed, but the methyl group attached to the carbon in the back is going to rotate 60 degrees, as you see. This one is a staggered form. Now as we rotate the second structure 60 degrees again, as you see here, we go back basically to the first structure, but this time the methyl group attached to the second carbon is going to be behind the hydrogen at the bottom right attached to the front carbon. You see, it is eclipsed again. So we're going to rotate it 60 degrees again. As you already know, this one is the methyl group attached to the carbon in the back is going to go at the very bottom this time. So as you see, we're going to draw the front carbon and all the attachments all over again. The CH3 on the top of the carbon in the front is going to stay fixed. We're going to put the methyl group attached to the back carbon at the very bottom. And we're going to attach the hydrogens after that. We rotate 60 degrees again. This time it's going to go back to eclipse. The CH3 attached to the carbon in the back is going to align with the hydrogen at the bottom left, right here where you see. We're going to rotate 60 degrees again. It's going to be the staggered form again. The CH3 on top is going to stay fixed as always. And this time the CH3 attached to the carbon in the back is going to go top left. And we add the hydrogens at the end. And once we do the 60-degree rotation, it's going to go back to the first orientation that it had before the first structure. So we're going to basically draw it again. So this is a 360-degree rotation of the carbon in the back with regards to the carbon in the front. So this time I'm going to draw a diagram of all these structures as you see here. Now you probably can guess which one probably has the most potential energy and which one has the lowest. But let's go slowly on this one. So we all can predict that eclipsed ones will have a higher potential energy. But this time we have, instead of 3 hydrogens on each carbon, we have 1 methyl group on each carbon with 2 hydrogens. So as you see in the first structures, the 2 methyl groups are aligning with each other. So this is the time that we have the highest potential energy. Why? Because these 2 methyl groups want to get rid of each other and get as far as possible from each other due to Vesper theory. So as you see, this one is going to have the highest potential energy. So we're going to label this as at the very top in our diagram. Now the third structure is eclipse again. So this one, although has a high potential energy, since there is no alignment of these two methyl groups, it is going to be still high potential energy, but not as much as the first structure. So we're just going to mark the diagram at a very high energy, but not as much as the first structure, a little bit lower. And with the fifth structure, again, it is eclipsed, so we expect a high potential energy from it, as much as the third one, but not as much as the first one, because in this one, like the third one, the methyl groups are not aligning with each other, they're aligning with the hydrogen substituent. So there is a high potential energy, but not as much as the first one, which two methyl groups are aligning. And the last structure, as you see, it is the first structure basically, so since the methyl groups came back to each other, this one's going to have the highest potential energy possible in this conformer. Now let's go to the staggered structures. You see here in the second structure, these two have a 60-degree angle from each other, so no substituent from these two carbons, the central carbons, are aligning with each other. So this one's going to have a low potential energy comparing to the ones that are eclipsed. And the sixth structure is basically looking like the second structure. It is not the same basically, the conformation, but or the arrangement, but as you see, they are 60 degrees apart from each other, so basically these two stagger forms have a low potential energy as much as each other, so we're going to label them in a way they align on the diagram. But the fourth structure, the methyl groups are 180 degrees apart from each other. This is the most stable and the lowest potential energy state of this spatial arrangement. So we're going to label this, or we're going to mark this on the diagram a little bit lower than the second and the sixth structure with the green one, as you see. As we're going to connect these dots to each other, you see how the trend of potential energy is as you rotate 360 degrees. And basically, the eclipse structures that did not have the two methyl groups aligned with each other, those should have the same potential energy. The same stories with the staggered ones, that the methyl groups were 60 degrees apart from each other. Those two should have the same potential energy too. So the first one we're just going to call it A, the second one B, third one C, fourth one D, E, F, G. So I can show you where which one is on the diagram. And by the way, A and G are basically the same. Don't get confused on this one. So the A is basically the highest potential energy, the same with G, and B is the low potential energy, but not as much as the fourth structure, not as much as D. C, D, E, F, G, as you see here. Now, as you see, as I'm marking these two structures with green arrow, B and F, the staggered versions that do not have the lowest potential energy, these are called gauche. So I'm going to repeat again. Staggered formation that do not have the lowest potential energy. These are called gauche. As you see here in structure D, the two methyl substituents are as far apart from each other as possible. So that makes them to have the lowest potential energy as possible. And that makes them the most stable, because as you see in structure A and G, the methyl groups try to get away from each other. That's why they have the highest potential energy at A and G. But since in D structure they're far away from each other as possible, in that case they have the lowest potential energy, and therefore they're going to be the most stable conformer of butane. So as I show you here in the diagram, the lowest energy is going to be for anti, and the two other that have low potential energy are going to be gauche. So let's write gauche and gauche, and anti for the lowest one. Okay, we're going to talk about conformers of cyclohexane. As you see, we have a hexane here in a form of hexagon. Now in a 3D world, we're not going to have necessarily a flat hexagon as hexane. We could say the most stable version of a hexane is what we call a chair model, which I'm going to show you right now. So in order to draw it, as you see, I marked the two parallel lines on top and bottom of hexane with orange, and we're going to draw the two parallel lines. And I'm going to use a dark blue and a dark purple color. As you see, I mark it on the hexane first, and then I'm going to connect it from the two orange lines, and we're going to connect them together to make an angle. Yeah, we connect them and we go downward from the orange lines, Now for the other side, as I mark it with red and blue, as you see, I draw them upward. So as you can guess, the blue line that I already drew is parallel to the dark blue on the top left. The red one is parallel to the purple one. Now in order to draw the substituent of these, as you see, if the connection is pointed upward, we're going to go one hydrogen up. So you see here, as I point here with the arrow here, this part is pointed up. So we're going to draw one line upward. And this is where the substituent is going to get attached to. Now it could be hydrogen. If it is hexane, it's going to be hydrogen for sure. If there's any functional group or any substituent, that will attach to it like this. So the next one, as you see, since it is pointed down, it's going to go downward, straight. And as you see, the one that I pointed there behind it, this one here is pointed up, so we're just going to go one line up. Now the last one, as you see, it is pointed down, we're going to go straight downward. This type of bond that can take a hydrogen substituent or a functional group, anything, we call these axial. Axial is basically closer to the center of that hexane. So it is important to remember like which line is parallel to the other one, because in chair shape, it is hard to see which line is parallel to which line. So as you see, the blue line is parallel to the dark blue one on the other side that I'm showing you with the green arrows. The red one is parallel with the purple one. I'm showing it with the black arrows. Now, so as you know, carbons take 4 bonds basically. We show 3 of them right now. So there's one more left. So in this case, the one that I'm showing you right now, we start with the far right on top of that point that I'm pointing with the arrow. You see, we're going to draw a line parallel to the orange lines. So we're just going to drag it down. As you see, I'm pointing it with the arrow, and it is parallel to the orange lines. Next one would be on the other side, on the left side of the chair molecule. As you see, it is the pointy part again. So this time we're going to drag it up, still parallel to those orange lines. So the far left and far right of the chair model is going to be parallel. We can have one axial substituent and one, as you see here, parallel to the orange lines. Next one, as you see, this carbon is pointed down for the axial. So this one is going to have a parallel to the green arrows, as you see on the dark blue one. I'm pointing it with a green arrow for you right there. So this one is going to be exactly parallel to that side. This one on the frontal carbon is going to be parallel to the purple line with black arrows on it. As you see, I'm pointing at it. The next one, as you see, the axial is upward. So this one is going to be exactly parallel to the blue line, and it's going to go downward. The pattern here is to have an angle of 109.5 degrees between each of these bonds. So as you see, I'm showing it with a green arrow again. This one is parallel to the blue line, and on the other side, this one is going to be parallel to the red line, which you see I'm showing it with a black arrow. I'm pointing at it. See, this is parallel to the red line, and this type of bond is what we call equatorial. So this one can still carry any kind of substituent, any kind of functional group, or even hydrogen if it is just a hexane. Equatorial, unlike axial, is going as far away as possible from inside the ring. So if most of your substituents are at equatorial, you're going to have a more stable molecule as a matter of the conformer of cyclohexane. And the most unstable is when all of your substituents are in the axial position. Okay, this is the chair model as you see. I'm going to label it as chair now. So after we draw the chair, we're going to go after the Newman projection. So I'm going to label the 3 left carbons of the chair model with light blue for the far left one that is facing downward, and black dots for the 2 carbons facing up with 2 axial carbons going upward. I'm going to show those with black dots. Why? Because as I told you in the Newman projections before, dot means this is the closest carbon to us and there's nothing hiding behind it. So we put a blue dot downward and 2 black dots on each side of it, a little bit upward. And we're going to connect these with a line to the blue dot. We basically picture the chair from the place that I is. After that, we're just going to basically draw the axial substituents. We're not going to attach anything to it. This is just hypothetical. If it is just cyclohexane, it's just going to be hydrogen, but we're not going to label anything on top of these bonds. So we're just going to draw the axial ones. As you see on the blue one, the axial is facing down. So we're going to draw a line down. For the 2 black ones going upward, so we're going to draw an axial going towards the top. And then we're going to go for equatorial. For the 2 black ones, as you see, one of them, which is closer to us, is facing toward us. The other one is going inside the page. So in the Newman projection, we're going to draw one of them like a little bit about bottom right and the other one about bottom left. And for the blue one, we're going to go basically, since it is going on the left in the chair model, basically that means in a Newman projection, it is coming toward us. But we're not going to use wedge or hash because this is not perspective. This is called chair model. So we basically draw a line a little bit towards the top because it's not going down, because axial is going down. If axial is going down, the equatorial is leaning upward. If the axial going upward, the equatorial is leaning downward. It's not going exactly down to the bottom or to the top, but it is leaning toward that direction. In the blue one, we're going to do the equatorial going upward and a little bit to the right to show that it is coming toward us. There is no perfect way to do it, but this is how you can do it easily. And the 2 carbons behind the 2 carbons that we drew already is going to be shown with a circle. As you see in Newman projection, the carbon that is hiding behind one carbon is going to be shown with a circle. To draw the axial carbons and substituents of it, we're just going to drag one line to the bottom from the circle. In order to draw the equatorial for the carbons in the back, as you see, since the axial is going down, the equatorial is leaning upward. So we basically draw the line from the circle, one of them going to the top right and the other one going to the top left. After that, as you see, the far right carbon that is shown here with purple, we're going to put a dot on top of the blue dot. So these 2 are not aligning with each other. The only 4 carbons that are aligning are the ones that are attached to the orange line you see, that I show them with a black dot. The purple one is going to be on the top side of the Newman projection. So we're going to basically attach the purple carbon to the black carbons, but bear in mind, it should be attached to the circle, not to the dots, because that purple carbon is attached to the carbons that are on the back side of our Newman projection. If that line passes the circle to the dot, that is absolutely wrong. You're showing a different structure. After that, as you see, the far right carbon has an axial going upward, so we're just going to draw a line going to the top. And the equatorial is leaning downward, going inside the page. So we're going to lean the equatorial downward, but we try to do it to the opposite way of the one that is attached to the blue one. So if the equatorial for the blue one is going to the top right, we try to do the equatorial for the last one to the bottom left. Next example, as you see, we're going to have a 1,3 dimethyl cyclohexane. So on the carbon number 1 and carbon number 3, we're going to have a methyl group. Now, at this point, it should be easy for you to draw a chair without labeling the lines with color. We're going to draw a chair, and at this point, we're going to number them in order for you to understand. So we're going to put the top right one as number 1, then 2 and 3. Each angle basically represents 1 carbon, as you see. So in this part, we're going to go with axial bond for the substituent. So we're going to draw a line going upward on carbon number 1 and carbon number 3, since they're both pointed upward. And at the top, we're going to write the CH3. And then we're going to draw the equatorial lines pointing in with hydrogen. As you see, I'm just going to draw all the hydrogens that are left here. Carbon number 1 and 3 are going to have 1 equatorial left, and we're going to put hydrogen at those places. So as we're going to draw the Newman projection for this chair, we're going to put an eye on the left side of the chair model, and we're going to look at it. So basically, like the last one, we're going to draw 3 dots. which represent the 3 carbons closest to our eye. We're going to connect them with 2 lines. The dot on the right side is basically our carbon number 3, if you realize. So it has one axial substituent of methyl. We're just going to draw this and put methyl on top. And so far, for the rest of the substituents attached to these 3 carbons, they're just hydrogen. So we're just going to draw all the axial and equatorials for these 3, and we're going to label them with hydrogen. After that, we're going to go with the carbons on the right side, carbon number 2 and carbon number 6. We're going to draw them with a circle. And the top carbon, which is carbon number 1, which has one methyl group attached to it, we're just going to put a dot on top. And we're going to connect those circles with the dots with carbon number 1. And we're going to connect those circles to carbon number 1. And as you see, carbon number 1 has a substituent of methyl attached to it with an axial bond. So we're going to draw a straight line upward with a CH3 on top. And the rest, as you know, is going to be hydrogen. So the rest, axial and equatorial bonds, we're going to draw them and put hydrogen at the tip of them. As you see, the 2 methyl groups are basically on the same side. They're pointing upwards. So this one is called a cis structure. Another chair model that we can draw is when carbon number 1 has an axial methyl attached to it, and carbon number 3 has an equatorial methyl attached to it. As you see, we're going to go upward again with carbon number 1, but with carbon number 3, we're going to do an equatorial leaning a little bit downward towards outside the page. And we're going to label the rest with hydrogen again. So as you see, this time, one CH3 is pointing upward, while the other one is pointing downward. Just to be sure, let's make the Newman projection as well. So again, we're going to draw the 3 dots, and we're going to attach it with 2 lines with each other. The dots on top is going to be our carbon number 1. And the 2 carbons that are behind are carbon number 3 and carbon number 5. We're going to draw them a circle, and we're going to attach them with a line to our carbon number 1. And since our methyl group is going upward, we're just going to go upward again. However, with the methyl group on carbon number 3, that one is going toward outside the page. So on the Newman projection, we're looking at it going to the bottom right. So going from the dot, since it is on the carbon number 3, we're going bottom right. We're drawing the line. That is our equatorial methyl. And the rest is going to be filled with hydrogen. This structure, since one of the methyl groups is going upward and the other one is going downward, regardless of being axial or equatorial, that does not matter at all. If one of them is going upward and the other one is going downward, that is called trans. Now, they both might be equatorial, they both might be axial. If one is going up, one is going down, that is trans. If they're both going up or both going down, that is called cis. Now here we're going to go with the concept of ring flip. So as you see, we're going to have a chair model here with 2 substituents, one axial as you see, and the other one equatorial. So in case there's a force being pushed at our ring from top and bottom, there is a scenario here that our ring might be flipped. So as you know, we call these conformers because the same compound can have different spatial arrangements. So as a force can come from up and down, our ring basically flips. And as you see, I'm going to draw the other chair. As you see, this one looks the opposite way. But as a matter of being right and left, we didn't rotate it. The carbon on the left side of this one is the same as the carbon on the left side of the first structure that we already drew. So in this case, the substituent that was equatorial in our first structure is going to be axial now. The same applies to the other one. The substituent that used to be axial in the first one is now going to be equatorial. As you see, I'm going to label these carbons for you. So the carbon on the left, I'm just going to draw it. I'm going to label it with blue, and the right one is going to be labeled with green. So the same applies to the methyl group on the right side. The one that was axial at first is now going to be equatorial. Now we're going to label it axial and equatorial. So this is what we call a ring flip. It could be either due to a force or any other reason. But the point is, if there's any substituent equatorial, it's going to turn axial. If there's any axial substituent, it's going to turn equatorial. Okay, now we're going to do some cis and trans examples. So as you see, we have a chair with a Cl and a Br attached to it, both equatorial. The question is whether it is cis or trans. So as I told you, it does not matter if they are both equatorial or axial or not. The only thing that matters is which way they're pointed at, downward or upward. So as you see, these two CLs as equatorial, they're pointed downward. I'm going to show it to you on the Newman projection here. So we draw the 3 dots and connect them with the 2 lines. The 2 carbons behind them are going to be drawn with circle, and the top carbon is going to be right there, and we're going to attach it to the 2 circles. Here, as you see, for both of them, in order to show them, for the CL, the equatorial is going to go downward. Why? Because the axial is going upward, so the equatorial naturally goes downward. As you remember, in tetrahedral, always, the angle is 109.5 degrees, so it's more than 90 degrees. So if the axial is upward, the equatorial is 100% downward. So for the carbon that has the CL is going to go downward. And for the Br as well, it's going to go towards the bottom left. So since they're both facing downward, this is going to be a cis structure. Now we're going to do another example. As you see, we're going to have a CH3 equatorial going upward, and we're going to have another substituent Cl being equatorial on the other side going downward. So as you see, I'm just going to draw the Newman projection for you. The eye is going to be on the left side, so basically a CH3 is going to be the one closest to us. So as always, we're going to do the 3 dots. We're going to connect them, the 2 circles, and the dots on top. So as you see, the Cl is equatorial, so we draw it downward. And the methyl group is equatorial too, but since the carbon that has the methyl group has an axial going downward, the equatorial for this one is going to go upward. So as you see, as we draw it, one is going upward, the other one, Cl, is going downward. In this case, we call this a trans structure. So for the last example, we're going to do another chair model, and we're going to have a CH3 going upward, and we're going to have a CH3 equatorial going downward. So without drawing the Newman structure, you can guess probably. One CH3 is pointed upward. The other one is equatorial pointed downward. This is automatically a trans. And you don't even need to draw the Newman for this. But I'm going to include it in the notes. Afterward, when you download the notes, you can have the Newman projection as well. But in some cases, when they give you the chair structure in the exam, it's better not to always be dependent so much on the Newman projection, because sometimes you need to decide fast and you have limited time. So as you can see here, this one, the CH3 on the 3rd carbon is going upward. The other one, which is equatorial, is going downward. Easy. It's going to be a trans, hands down. So as you see, the carbon number 3 has one going upward and the other one has an equatorial. So I'm going to draw the equatorial going downward with a methyl group. And the other one is going to be the axial one going upward on the dot which is closest to the eye. Another CH3. So hands down, this is a trans structure.